Hello, this is Ms. Moore, and today during chemistry we're going to discuss molecule polarity. So today's essential question: what makes a molecule a polar molecule? So here we go. Molecule polarity. Like a polar bond, a molecule can be polar with partial negative and positive charges. Remember the dipole moment. But now we're talking about this dipole moment, not necessarily with the bonds, but with the whole molecule. Okay? So the polarity of a molecule depends on two things. Important. The electronegativity difference between the two bonded atoms, and this is basically what we're talking about here, is whether or not we have a polar bond, and the arrangement of all the atoms in the molecule. And that's the new part. So it's actually possible for a nonpolar molecule to contain polar bonds. And that's because the dipole moments of polar bonds can possibly cancel each other out depending on the arrangement of the atoms in the whole molecule. So these polar bonds, the dipole moments, can cancel out and you end up with a nonpolar molecule. All right, so let's go through the list of the steps, I guess, of how to determine the polarity of a molecule, determining the polarity of a molecule, and then we'll actually try it. And it'll make more sense after we try it. So step one is you need to draw the Lewis dot structure for the molecule and determine its geometry. Okay, its Vesper geometry, meaning its shape. Okay, you need to identify any polar covalent bonds. And then I guess I should have put this in the list, but you should show the dipole moments. Remember, with like the plus sign with the arrow pointing to the I'm not giving myself enough room, so the arrow points towards the more electronegative. Atom. So it'll be the negative dipole moment. Okay. And then determine if the polar bonds add together to form a net dipole moment. And if you have a net dipole moment, that means you have a polar molecule. Or if the dipole moments cancel out, meaning you have a nonpolar molecule. Okay, so the next step is to actually try several of these, and hopefully this will make more sense. All right, let's try a couple problems. We'll start with CO2, or carbon dioxide. So carbon has 4 valence electrons. Oxygen has 6. And when we draw the Lewis dot structure, we'll end up with something like this. And then for the shape, we look around the central atom. We see that there's 2 bonding regions, or 2 electron domains here and here. Both bonds, no lone pairs. So we end up with a linear molecule. Okay, so Now we need to see, are these bonds, this carbon-oxygen bond, polar or nonpolar? Well, they're not the exact same atom, right? We've got carbon and oxygen, so they're polar. They're not super far away from each other, so probably not real polar. Oops, let's go back up. With the oxygen being the more electronegative atom, which means the electrons are going to pull away from the carbon, making the carbon slightly positive, and towards the oxygens, making the oxygens slightly negative. Okay, so now we know we have a linear molecule made up of two polar bonds. The question is the molecule polar or not? And this is where it takes a bit of thinking. I had to pick a different color here. How about orange? Okay, what you'll notice is that the dipole moments are equal and opposite, right? We've got carbon, this first one, the oxygen is pulling the electrons towards itself, and on this side, the other oxygen is pulling the electrons toward itself, resulting in equal and opposite pulls, which means the electrons aren't actually going to move anywhere at all, which makes this a non-polar molecule. Okay, so that what's really happening here is that the dipoles are canceling each other out. Okay, so here we have an example of a molecule made up of polar bonds that is non-polar. All right, let's try another example. Let's try water, or H2O. All right, so we have two hydrogens, each of which has one valence electron, and oxygen has 6 valence electrons. When we put them together to form our Lewis dot structure, we'll end up with something like that. Now, for the shape, we have 4 electron domains, 2 bonds, 2 lone pairs. That's going to end up giving us a bent shape. So, more like, let's see, we'll have hydrogen, oxygen, hydrogen. So more like that. Ooh, ugly drawing, but hopefully you get the point. All right, so let's decide if our hydrogen-oxygen is polar or non-polar. Well, they're not the same atom, right? We've talked about this. Really, any bond is going to be polar, except for carbon and hydrogen for us. And if it's 2 atoms that are the same bonded to itself. So this is going to be a polar molecule. Which one is more electronegative? Let's go back up here. We've got oxygen and we've got hydrogen. And if you remember, the electronegativity of hydrogen puts it more in this region here. Either way, oxygen is more electronegative. So that means that the electrons are pulling towards the oxygen, giving us hydrogen is going to be partially positive and oxygen is going to be partially negative. So we definitely have 2 polar bonds here. What about the molecule? Is the molecule polar or nonpolar? Well, looking at the dipole moments, they're both pulling towards the oxygen, right? Meaning that the dipole moments are actually adding up. So the regions down here of the molecule are going to be partially positive, and the region up here is going to be partially negative. So our molecule is definitely a polar molecule. So here's an example of a molecule made up of two polar bonds that is indeed polar. All right, let's try another one. How about carbon tetrafluoride, or CF4? So carbon has 4 valence electrons. Each of our fluorines has 7. So when we put together our Lewis dot structure, we'll end up with something like this. I do despise valence electrons, or at least drawing them. Okay. Our shape, we have 4 electron domains, all of which are bonds, which makes our shape a tetrahedral. Okay, and let's check to see if our bonds are polar or nonpolar. And we know they're going to be polar because they're not the same atoms. So which atom is more electronegative, the carbon or the fluorine? Well, we've got carbon and fluorine. Fluorine is more electronegative, which means our dipole moment will be the electrons pulling towards the fluorines. Okay, so we have a tetrahedral molecules made up of 4 polar bonds. Question, of course, is the molecule polar or nonpolar? Well, look at this. Let's pick a different color, purple. Okay, if you look at this right here versus that right there, our dipoles are pulling in equal and opposite direction, which means they basically cancel out. And the same thing going across. That means that even though we have a molecule made up of 4 polar bonds, our molecule is non-polar. Okay. I hope you're starting to feel a little bit more comfortable with this. I do want to try one more though. All right, last one. Let's try F, we'll use F again, PF3. So phosphorus has 5 valence electrons. And our fluorines, once again, as is true of all halogens, has 7 valence electrons. So when we draw the Lewis dot structure, we'll end up with this. And for our shape, we have 4 electron domains, 3 bonds, 1 lone pair, which makes our shape pyramidal. Pyramidal. Okay. Our bond is definitely polar, right? So we have 3 polar bonds. And let's check to see which atom is more electronegative. Whoops, sorry. Try that again. Okay, we've got, nope, not carbon. We have phosphorus and fluorine. Fluorine is definitely more electronegative, which means our electrons are going to be pulling towards the fluorines. So we have 3 polar bonds. So is the shape polar or nonpolar? Is the molecule, is the molecule polar or nonpolar? Well, it looks like those two basically cancel out. However, that one does not, which means our molecule is indeed polar. All right, folks, I hope you're starting to get the pattern. That's it for today. Have a good one.